one of the things that an aircraft designer always have to keep in mind is about how an aircraft is going to behave in motion with respect to external disturbances, and the disturbances can be small or large. When we talk about disturbances and the motion, the aircraft response with respect to those disturbances, we are talking about aircraft stability. Stability is a property of any equilibrium state of a system. In this case, our system is okay. Let me repeat what we are interested in looking at. We are interested in looking at how an aircraft which is flying in equilibrium responds to any external disturbance which can be coming from wind, for example. So, how an airplane flying in an equilibrium state responds to disturbances, for example, gust of wind, is related to its stability characteristics, and that stability characteristic is a property of that particular equilibrium condition that the aircraft is flying in. So, let us try to define what equilibrium is. So, as we know, an equilibrium state can be a position of rest or a dynamic condition with uniform velocities. So, that also means with no acceleration involved. Mathematically, this translates into these two equations. So, sum of all external forces acting on the body are balanced, so that net acceleration is 0, and that gives that results in V equal to constant. So, if an aircraft is flying at constant velocity, uniform velocity, then we say that the aircraft is in equilibrium. Added to that, we should also have this condition satisfied, which is added to that condition. We should also have this satisfied, because the aircraft is a 6 degree of freedom is having 6 degree of freedom motion, 3 in translation described by these 3 force equations, and this F is a vector consisting of the motion in the 3 along the 3 axis of the aircraft, and the moments which are resulting in 3 angular motions of aircraft. This also means if omega is the angular velocity vector, multiply that by this inertia, that equal to 0, this ratio is giving the angular acceleration. So, if the sum of external moments are 0, then what we arrive at is this. So, a dynamic equilibrium condition will be represented by a uniform velocity that can be translational or angular. Let us look at some of the flying equilibrium states of aircraft. So, example of such equilibrium states could be for example this cruise level flight. So, aircraft is moving with velocity v along its x axis, and thrust is also acting along the x axis of the aircraft. So, the equilibrium state and the corresponding equation are just balance these forces in the x and z direction, and what we get is so if I say u is the forward velocity, so this velocity vector is or we can just write this as u. All right. So, if you write down the balance of forces in the x and z direction, what you get is and this change in u with respect to time we have to set to 0 to find the equilibrium condition. In the z direction, similarly you have, so w is the velocity of aircraft in the z direction, and that gives you, and this also has to be set to 0 to get the equilibrium condition. So, in equilibrium conditions with degrees of freedom both in translation and rotation, for this case, so here we are talking about a longitudinal flying condition, which is cruise level flying condition. The equilibrium state can be defined by these two balance of forces, and the moment about the CG also should be 0. So, these three equations. So, this M here is the pitching moment about the CG in this longitudinal plane of aircraft is the pitching moment, and these are the forces acting on the aircraft. So, these three equations define the equilibrium state. Let us look at another example. So, this example is also from longitudinal flying condition, and here the aircraft is climbing. Gamma is the flight path angle. This W is the weight of the aircraft. L is the lift. Drag is acting against the forward motion. So, this is the Z axis. Okay. So, let us try to write down the component of forces acting along x and z direction. So, we will again assume that thrust is acting in the along the x axis of the aircraft, and V is this velocity vector, which is again having only the velocity component in the x direction. So, you can write the equation of motion along the x axis. Thrust, which is taking it in the forward direction, and there are forces opposing this motion, and they are a component of weight along drag, which is opposite to this x axis. All right. So, this has to be set to 0 to find the equilibrium state, and the motion in the z direction is given by this has to be 0 at equilibrium state, and the moments also have to be balanced. So, this condition is still active. So, these three equations will define the equilibrium state of aircraft in steady climb. This defines these three equations define the equilibrium state in level cruise condition, and if you want to look at any a non longitudinal equilibrium state, it can be, for example, a steady level turn state. So, what is happening in this case is bank angle is a constant, for level condition flight path angle has to be 0. On top of that, if you want to say coordinated level turn state, then we can also add this condition which is side slip angle equal to 0. So, this will also constitute one equilibrium state, which is a non longitudinal equilibrium state. Okay. So, what we want to understand now through this is, we want to look at when the aircraft is flying in one of these equilibrium states, and a small disturbance hits the aircraft, how it is going to respond to that disturbance, and that is the subject of stability. Stability has two notions, one is static, another is dynamic. So, we will first look at what static stability is, static stability of an equilibrium point, and what is dynamic stability. We will try to understand the difference between the two and see where they are useful in flight dynamics. These concepts are applicable to any system, any physical system, not just to the airplane. So, let us look at what I said in the beginning was that stability is a property of an equilibrium state, right. So, we have to look at first an equilibrium state and see how a system, when disturbed from equilibrium state, responds to the disturbance. So, the stability refers to the system's property to come back to its original equilibrium state when it is disturbed from there. So, look at simple examples. Let us look at example 1. So, we have, let us say in this case, ball sitting on top of this hill. There is another situation when this surface is now flat, and the ball is sitting at this position. So, this position is a static position of rest or equilibrium position of rest. We can also have this kind of curved surface which is like a well, and a ball is sitting at the bottom of this. Now, let us look at what happens. So, these three positions are equilibrium positions. So, ball is in position of rest in 1, 2 and 3. So, this is 1, 2 and 3. Okay. We will also assume that this surface is smooth, does not offer any resistance to the motion of the ball. There is a very it's not a realistic assumption, but this simplifies a lot of things. So, we want to look at how this ball is going to behave when the ball is hit from disturbed from this equilibrium position. So, the ball is hit. So, we know that the ball, when the ball is hit from this side, ball is going to have a motion which is going to make it fall. So, what is happening in this case is, when we disturb this ball from its equilibrium position of rest, it starts going away from this position. When this happens, we say that this equilibrium position of this ball is unstable. When you hit it from the other side, it is going to fall to the other side. So, this position of equilibrium is unstable for this ball. Now, let us look at what is happening here. Here, when you hit the ball, it is going to go away from this equilibrium position and going to acquire another position. So, in such a case, we say that that the ball is neutrally stable, or the equilibrium state of this ball is neutrally stable. In this case, when you hit the ball from this position, it uses that energy of the disturbance to rise along this wall of the well and goes up to some point, and once it has lost that energy, it starts coming back. Similar thing will happen on the other side. So, what is happening in this case is, the ball is trying to come back to this equilibrium position. So, this equilibrium position is a stable equilibrium. So, right now what we are saying is, we want to look at how the system is responding to a disturbance. We are not saying whether it has really achieved its original state of equilibrium or not. So, static stability refers to systems, ball or the aircraft, tendency to return to its original state. Static stability refers to system's tendency to return to its original equilibrium state. So, clearly in this case, it does not have any tendency to come back to this equilibrium state. So, we say that is unstable. In this case also, it is going to go and acquire another equilibrium state. So, that is why it is neutrally stable. Here it has a tendency to come back to its original equilibrium state. So, we say that this is a stable equilibrium state for this ball. Let us look at another example. So, here we have a pendulum. So, bob of mass m hanging at one end of this wire of length L, and this O is the suspension point. So, this clearly is an equilibrium state, which is also the position of rest for this pendulum. Now, let us see what happens when we hit this bob from this equilibrium state. So, it is going to go away from this equilibrium state and acquire depending on the energy of the hit, it is going to take a new position. See what is happening at this position to the forces. We will also associate one variable theta with this displacement from this equilibrium state, which is, we will see how we get this from the equation. So, normal to this line is the path of this m representing its motion, and we want to write down the equation of motion for this motion of mass m. So, F is here minus of mg sin theta, and let us try to write down the moment equation for this case. So, we are trying to write down the equation of moment around the suspension point. So, less so this pendulum is having an angular motion about the suspension point, and I is the inertia of mass m, rotational inertia of mass m. The equation of motion is okay. So, positive theta is this, and so positive moment is this and negative moment is this. So, here this is the acceleration, positive acceleration and angular acceleration, and into I is giving the moment in this positive direction, which is balanced by this force mg sin theta into L in the negative direction. That is why this negative sign. I is ml squared. So, from this equation what we get is so this is the equation of motion of pendulum shown in the picture. To define the equilibrium state for this pendulum, what we have to do is we have to either set the sigma m to 0, or we can also set all the variables the derivatives of variables with respect to time to 0. So, in this case this rate of change of any variable with respect to time is 0, that is another definition of an equilibrium state. So, in this case what we get as the equilibrium state is the result of this equation. So, sin theta equal to 0 has solution which is n into pi and can be and so on. So, n is an integer. So, physically it looks like that there are two equilibrium solutions possible, and they are actually n can be so the pendulum can go in the other direction also. So, we can have solutions for this case as these are physical solutions and this is the mathematical solution. So, here we have 3 equilibrium states, 2 of them are actually same. So, one equilibrium state is theta equal to 0 and the other equilibrium state is vertically up position of this mass m. Now, let us look at what is happening to this force when theta is changing. What we want to know is how this force is changing with respect to the angular displacement of the pendulum. Now, from this equation what we get is and as I said the equilibrium stability is a property of an equilibrium. So, we have to look at how this force is changing around the equilibrium states. So, remember this force is developing only because of the motion of this mass m. If this theta is 0, there is no force. So, this force is developing because of the displacement of the mass m, and it is called restoring force. So, if you look at the derivative of this force, which is being developed because of the motion of the mass m, derivative of this force with respect to the displacement variable is minus of mg, which is less than 0. So, what it tells us is when theta is going up or increasing, this f is going down. So, that is what this derivative is telling. So, this force is actually acting in the direction to decrease the angle theta, and that is when we say that this equilibrium state around which I have done this is a stable equilibrium state. Now, let us look at what happens. So, this is 1 and these are 2. Now, let us look at what is happening at equilibrium state. So, that is the vertically upward position of mass m. Del f over del theta is plus mg in this case. Now, here what is happening is when the ball is disturbed from this equilibrium condition, this force along the motion of the ball along the increasing direction of theta is going to grow. So, it is actually taking the ball away from the equilibrium condition, and that is when we say that the equilibrium state 2 is statically unstable. So, what is happening in this case is when with theta, this force in the direction of increasing theta is growing. So, it is going to further increase theta, and theta is the disturbance. So, it's a change in it's a change from this equilibrium state. So, what is happening in this case is theta is growing, this force is also going up and helping theta to grow further, and that is when we say that it is going to go away from the equilibrium state 2, which is theta equal to pi or minus pi, and therefore, the equilibrium state 2 is statically unstable. Now, this example 3 is from aircraft dynamics. So, here we are looking at this aircraft which is flying level, having only velocity component in this x direction. So, in equilibrium thrust is equal to drag and lift is equal to the weight of the aircraft, and let us say sum of all external pitching moments is also equal to 0. So, this in this situation, what we want to study is to look at if the aircraft is statically stable with respect to disturbances or not, and this we are only doing graphically. So, here we plot thrust and drag versus speed of aircraft. Drag profile is parabolic, and this drag has to be overcome according to this equation. So, the thrust available should be able to overcome the drag. Let us say we draw this for a jet engine. So, thrust is almost constant with respect to the velocity. So, this is my thrust available, and this is drag. So, where these two curves meet, we are satisfying thrust equal to drag condition, and that is our that intersecting point is our equilibrium state. So, this is equilibrium state 1, and the other equilibrium state is here, which will mark as 2. Okay. Now, let us try to look at the stability properties of these two equilibrium states. So, 1 and 2 are equilibrium states. We can look at stability with respect to all variables involved here in this longitudinal plane, but here we will restrict ourselves to change in speed in the forward direction. So, let us look at what is happening to this equilibrium state. So, let us say there is a change in speed in the so there is a disturbance which is causing a change in speed from this equilibrium state. So, that now aircraft speed has increased to this point from this equilibrium state. Now, when this happens, what is happening here is drag is going to go up, it is going to change because of this increase in speed, it is going to go up according to this curve, and it becomes more than the thrust which is available. Right. So, automatically there is a deceleration of aircraft which is trying to bring it back. On the similar regions, when the perturbation results in change in velocity in the negative direction, so the velocity is reducing, speed of aircraft in the forward direction is reducing, then the drag goes down and the aircraft will accelerate because thrust available is more than the drag now. So, let us put a arrow like this. So, in both situations we see that the tendency of the aircraft is to come back to this equilibrium state. So, change in speed is resulting in aircraft trying to reduce that change in speed, and then we say that this equilibrium condition 1 with respect to the change in speed is stable, that is statically stable. We can give the same arguments on this side also for equilibrium state 2. So, this is your V equilibrium 2, V equilibrium 1. So, if there is a decrease in velocity in this case, now drag is again is more than the thrust available. So, aircraft will decelerate. So, it is going to take it away from this equilibrium condition, and the other side giving the similar argument, the aircraft is going to go away from this equilibrium condition. So, this equilibrium condition is statically unstable with respect to the change in speed due to the disturbance. Now, let us look at what happens when you change the thrust available. Thrust available will also change with altitude, and when you go to higher altitudes, it is going to thrust available is going to go down, and there will be one this line is going to be almost parallel to the first one. Okay. So, let us try to change the thrust available. We see that there is one thrust condition which is resulting in a single equilibrium state, and that is associated with the velocity which is resulting in the minimum drag. Now, this case is of a neutrally stable equilibrium state, because here what is happening is when the speed is increasing on this side because of the perturbation and drag is more than the thrust available, and this is what is happening. On the other side also it is the same thing. So, this is a neutrally stable equilibrium state, and any equilibrium state for the thrust available higher than the minimum drag, any equilibrium state on the back side of this curve is unstable and on the other side is stable. But in reality this is what it tells us is that whole of this part of this curve where we can find several trim points by changing the thrust available are not available for flying, they are all unstable, and on this side it is all stable. In reality this is not what happens, and we will talk about it when we come to dynamic stability.